Welcome to the AICE Chemistry lecture series. Today we're going to look at Chapter 4, Section 3, which focuses on covalent bonding. Now this is going to be the beginning of a very long conversation about covalent bonding that we're going to talk about in not just this chapter but in coming chapters as well. Covalent bonding is a major focus on a lot of what we do in this class, because we're not just talking about molecules, which is what we're going to focus on here, but we're also going to talk about much larger later on organic compounds that are all covalently bonded. So this is going to incorporate not just a conversation about covalent bonding, but the types of bonding later, as in sigma and pi bonding. We're going to talk about intermolecular forces. We're going to talk about polarity and a lot of different aspects that only happen in covalent bonding. So be ready for that much longer conversation and be ready to do something that you might not be used to, which is tying a bunch of topics together when we are looking at covalent bonding. Now, when we look at covalent bonding, we have to start by just defining what covalent bonding is. Covalent bonding usually is going to happen between two non-metals, although it can happen with metalloids sometimes, but most of the time we're going to be looking at non-metals. And when covalent bonding happens between non-metals, what's going to happen is that they're going to share one or more pairs of electrons to form a covalent bond. Now this right here is a key word, which is pairs of electrons. Not just single electrons, but pairs of electrons. This is key because covalent bonding and bonds never happen with a singular electron. They're always going to happen with two electrons at a time. And you'll see the theme that in covalent bonding, when we're drawing Lewis structures, dot and cross diagrams, electrons are always paired up because unpaired electrons are not stable in nature. Electrons want to be paired up to an orbital in order to have a more stable configuration in the atom itself. That's one of the reasons why when we are looking at the octet rule has electrons be 8 electrons in the valence shell usually. There are exceptions to that because of that pairing going on. Now covalent bonding, like I mentioned, is the electrostatic attraction between the nuclei of two atoms that share those electrons. Because, again, we said earlier in section 1, bonds in general are always going to be some kind of electrostatic or magnetic attraction. They're always going to be the attraction of something that's positive to something that is negative. So if we make here, let's go make us a word here. If we grab two atoms, so we got atom number 1 here, and then atom number 2, and those atoms overlap with each other. If we have the nuclei of those atoms, the positive nucleus at the very center of the atom, so positive nucleus here, positive nucleus here. So these two atoms have positive nuclei and they share electrons in this overlap. What is actually keeping these two atoms together, like we explained in section 1, is not the overlap itself, is not the fact that they have a physical connection, because remember, atoms are not really all that physical, they're mostly empty space. What's actually keeping these two atoms together in this covalent bond is the fact that this positive nuclei is attracted to the electrons. Let me just put one arrowhead. It's attracted to the electrons that the two atoms are sharing, as well as the nuclei of the other atom is attracted to those electrons. So the actual bond between them, the actual covalent bond, is not just the sharing of the electrons, but it is the magnetic interactions that happen because of that sharing. Because of these electrons being shared right in the middle of the two atoms, the nucleus or the nuclei of each atom is attracted to those electrons, keeping those atoms in place. That's what the covalent bond actually is. Not the sharing, but the attraction of the nuclei for those shared electrons. Let's go back to our PowerPoint. So a few pieces of terminology that we need to be familiar with when it comes to covalent bonding. Covalent bonding, the electrons, like we said, are always paired, and they can be falling into two different categories for the valence electrons. When we're discussing bonding, we don't care about inner electrons. We're always looking at valence electrons, because valence electrons are the ones that we learn in honors chemistry that actually interact, that actually are part of bonding and chemical reactions. So those electrons can be in bond pairs, meaning that they're electrons which are shared between atoms. These are the electrons that we just discussed. So electrons, those valence electrons can be part of bond pairs, which are, again, in between atoms, or they can be part or non-bonding pairs, or what we call sometimes lone pairs. And these are pairs of electrons in the outer shell, in the valence shell of an atom, that are not involved with the bonding. Because the idea here is that when we have a very simple molecule like water, let's draw water here, we have oxygen with the two hydrogens, and then we have two lone pairs of electrons. So something we need to remember, this bond right here is made out of two electrons. These are what we call the bonding or bonded pairs of electrons. Whereas these electrons are not bonding, they're not between atoms, they simply belong to the oxygen. These are what we call lone pairs of electrons. They're electrons that are paired up but not between atoms, they just belong to one individual atom. And again, we can call these lone pairs, which is my preferred term and the term that I will mostly use here, or non-bonding pairs, which is a more direct and a clear term. Now, bonding pairs can be shared in multiples, meaning that yes, they have to be pairs, meaning that they have to be groups of two electrons, but we could have multiple pairs be shared. So we can have a single bond, which is what we're looking at here, where it's one set of shared electrons, or two electrons being shared. We can have a double bond that we learned about last year, where two sets, and that's where the double comes from, two sets of shared electrons are present, meaning 4 electrons in total. And that will happen in something like oxygen, where we have oxygen double bonded to another oxygen. And this double bond represents 4 electrons, or 2 pairs. Or we could have a triple bond. And a triple bond is simply just 3 sets of shared electrons. So we have something like nitrogen and 2, where we have, again, that triple bond representing 6 electrons that are shared, or 3 sets. That's where, again, the term triple comes from. So yes, covalent bonding is a sharing of electrons. Those electrons always have to be paired up. But there's no reason why we can have more than one pair, like with a double bond, which has 2 pairs, or 4 electrons in total, or a triple bond, which has 3 pairs, or 6 electrons in total. Now, this again should not be anything new to most of you, because we did discuss these topics in honors chemistry, but it is always good to refresh the brain and to start thinking about things slightly different, like the idea of talking about covalent bonds as the electrostatic attraction between the nuclei and those shared electrons. Not just the simple act of sharing electrons, but the magnetism that results from the share. Now, we did discuss dot and cross diagrams in the context of ionic bonds in the last section. We can also use dot and cross diagrams to show the sharing of electrons for covalent bonding. And some would argue that this is actually even more important than it is for ionic bonding, because we can see where the electrons came from for those bonds that are being shared. So both of the electrons come from one atom, or each atom put in 1 electron, how many electrons are being shared, so on and so forth. When we're doing dot and cross diagrams for covalent bonding, one of the things that you'll notice is that we'll show the bond itself as an overlapping of the valence shell, overlapping of the energy levels, in order to denote that the electrons in that overlap are being shared. Now, in some cases, we can have molecules where we have more than two atoms, and I will show you an example later on. But in the case where we have a molecule where there are more than two different types of elements, we can use other shapes such as triangles or open circles to show the electrons from the extra atoms. So let's look at these dot and cross diagrams. Now, most of the time with dot and cross diagrams, we will choose different atoms to have the different shapes. So hydrogens will all, for example, be, oxygens will all be here, have X's or crosses, whereas the carbons all have circles, or in this case here, the carbons all have circles where the hydrogens have crosses. And notice how every hydrogen has a cross. Well, if we have a case where we're looking at the bonding of the same atom, like in a hydrogen molecule, H2, then if we have two hydrogens, then we would want to assign each hydrogen a different shape. So dot and cross diagrams are only effective if we have dots and crosses. So if we're trying to show the overlap or the bond between two hydrogen atoms, we will give one hydrogen the X, one hydrogen the dot. And so when we show the hydrogen atom, notice how we have here the overlap in the middle, in the center, that has the one dot and the one cross, the dot from one hydrogen, the cross from the other. Now, in most cases, we wouldn't use the same or different shapes for the same element. Here, for example, when we're talking about looking at carbon dioxide is made of carbon and oxygen. So we'll choose to use dots for the carbon and X's for the hydrogen. So we can show here how hydrogen has 6 different X's. It's kind of hard to see here, but there are 6 different X's there. Let me maybe draw them in a little darker with a different color. So here we have 1, 2 X's. Here we have another 2 X's. So and then here another one and another one. So it's 6 X's in total, showing the 6 valence electrons. And then the carbon has 4 dots. When we then look at the carbon dioxide, you'll notice how we show that overlap of the carbon to the oxygen. And in that overlap, for each carbon and oxygen, we have here the oxygen with 2, 4, 5, 6 X's, and then the 2 dots that come from the oxygen, from the carbon itself. And then here, same thing with the other oxygen. This allows us to see that the bonds for the carbon dioxide are actually going to come with 2 electrons in that double bond, because this is a double bond, because it has 2 pairs, or 4 electrons in total. 2 of those electrons come from the carbon, we represent them as circles, whereas 2 of them come from the oxygen, which are here represented as X's. And we're gonna go into how to kind of put things together in a second after we're done looking at this. I'm gonna show you a few examples by freehanding them. And then here with ethane, which has 2 carbons and 6 hydrogens, again, we can see how each carbon has the dots to represent the electrons that came from the carbon. So dot, 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 dot. Carbon has 4 electrons. Hydrogen has X's, and it has 1 X each, because again, hydrogen being group 1 has 1 valence electron. And we can see here how in this structure, the bonds between carbon and hydrogen have 1 X and 1 dot each, because they're formed between 1 electron for carbon and 1 electron for hydrogen. But the carbon bond is made out of 2 dots. Why? Because both of the carbons put in 1 electron, and carbon electrons are represented as dots. All right. The last part here is to realize that we can actually transform these dot and cross diagrams to what we call Lewis structure, or displayed formulas that we learned about last year, by simply using, instead of dots for the dots and crosses for the bond, we can change those to lines for every pair of shared electrons and leave those outer electrons, or those unpaired electrons or lone pairs, as dots. So we can see here, and this is actually missing a few dots, I'm gonna add them in. We can see here for the carbon dioxide how that connected. How the carbon-oxygen bonds, which are double bonds, got replaced by two lines to draw the Lewis structure, and how those oxygens had their lone pairs of electrons be transformed just to simple dots for the pairs, which shows the lone pairs of electrons. This is what we call a Lewis structure, or a displayed formula that we learned how to draw last year. So let's look at some examples to kind of like put all of this together from a very simple molecule. So let's say we're asked to draw the structure for PCl5. Oops, I'm still using black here. Let me use white. For PCl5. What we'll have to do here is figure out how many valence electrons each of these have. So we're going to use pink here for phosphorus. Phosphorus is a group 5 or 15 element, meaning that phosphorus has 5 valence electrons. Now we can choose either dots or crosses here. It doesn't really matter, so I'm going to choose crosses. So phosphorus has a valence shell with 5 valence electrons. I'm going to put here 1, 2. Oh, let me use a different color. Let's do the electrons in white. So 1, 2, 3, 4, 5. Notice I'm going in a circle, right? I'm not pairing them up until we have 5. That's something we learned last year with dot structures, where when we are adding these electrons, we add the 4 electrons before we start pairing them up. Because that's how it actually happens in nature. Electrons are not paired up until we have at least 4. And this actually goes back to what we discussed in the last chapter, because the valence shell consists of the s orbital, or the sublevel, and a p sublevel. Doesn't matter which of these elements we're looking at, we consist the valence shell of an s sublevel and a p sublevel. So if we think back to Hund's rule, when we're filling this up, we're going to fill this up with 1 electron each before starting to pair them up. Now, there's a reason why this normally Hund's rule will only apply to 1 p sublevel. There is a reason why this happens across the S and the P, which we'll discuss later on when we discuss hybridization. But this is why we put 1 electron, 1, 2, 3, 4, 1, 2, 3, 4, before we start pairing it up into the S sublevel here for phosphorus. So just to remind you of why we're not pairing this up right away, and we're waiting until we have 5 or more. And then for chlorine, chlorine is a group 17 element. Being a group 17 element, chlorine has 7 valence electrons. Now we have, let me not do PCl5, I'm sorry, let's do PCl3, and we'll discuss why PCl5 exists later on in the chapter. But doing PCl3, we have 3 of these chlorines that have 7 valence electrons. So if we draw them out, we have Cl, 1, 2, and the placement is important, I'll go over in a second, 3 chlorine atoms. And we're going to use dots in order to do these chlorine atoms. So here we have, again, 7 valence electrons. So we have 1, 2, 3, 4, 5, 6, 7 valence electrons. We're going to have the same thing here. We have 1, 2, 3, 4, 5, 6, 7. And then finally here we have 1, 2, 3, 4, 5, 6, 7. Now that we have this, we can start putting together the structure, right? If there's something you remember from honors chemistry, you should remember that if we have electrons that are not paired up, and let's use a different color here, we'll use green. If we have electrons that are not paired up, those are the electrons that are going to create the bonds. So we're going to create a bond here, a bond here between these unpaired electrons. That's why it's important to only pair up the electrons after we have 5 at least, or after we have completed 4. And then here's another pair of electrons that are going to be paired up to form the covalent bonds. Well, if we put this together, what we end up with is a molecule where these electrons are going to be shared, these electrons are going to be shared, these electrons are going to be shared. And so, let me see if I can move these. I thought I would be able to, but I don't think I can. So this is going to end up having a molecule where these electrons are going to be overlapped in order to create our bond. So I'm going to do that here. I'm going to move this chlorine over. And again, by moving this chlorine, we're going to have this chlorine overlap with the phosphorus. I'm going to do this by using circles. I'm going to have another chlorine. So I'm going to erase this one. I'm going to overlap it. And then another chlorine here. That I'll move this one over here. So now I can draw my electrons and I can draw my chlorines. So this is Cl. This is Cl. This is Cl. And then I can draw in my electrons. Remember, the chlorine electrons were dots. So we had here 2 dots, 2 dots, 2 dots. And then the one that's now being shared. 2 dots, lone pair, and then the shared pair of electrons. Then here again, the shared pair of electrons, and then 1 lone pair, 2 lone pairs on this chlorine, 3 lone pairs on this chlorine. And this is the dot and cross diagram for PCl3, where we use the dot and cross diagrams for the individual atoms, the phosphorus and the chlorine atoms, to see where those unpaired electrons will be, and then pair those up by overlapping the diagrams and creating this dot and cross diagram for the overall compound. That gives us our dot and cross pair. Now, or dot and cross diagram. Now, if we had a third element, so let's say that this chlorine was not chlorine. Let's say that instead of doing PCl3, we were doing PCl2Br. Now, this is actually a very simple switch. Why? Because we're replacing one of the chlorines with bromine. Bromine is also a group 17 element, meaning that the structure of bromine is going to be exactly like the structure of chlorine. Both of them being group 17 elements means that they will both have 7 valence electrons. So the only real difference here is when I draw bromine, which I will draw in a different color. Let's do this reddish color. When I draw bromine, again, I will have that overlap. And I will have 7 valence electrons. What we don't want to do, however, is draw the valence electrons of bromine as circles. Why? The circles represent the electrons of chlorine. So we'll just choose a different shape. I could use a triangle. My preference is usually to use an open circle. So we'll do open circles for bromine. Open circle, open circle. We still have 7 valence electrons, which means that we're still creating that one bond with the phosphorus when we use bromine instead of chlorine, with that pair of bonding electrons. The only difference is that instead of now this being a dot, like when we have chlorine here, we're using an open circle to represent a third type of element. If we had a fourth element, we would just use a different shape. We will use a triangle, or we will use a square, or we will use a star. It doesn't matter what the shape is. What matters is that it's different from the crosses and dots. I like to use open circles because they're very obvious, they're very easy to draw. But again, you could technically use any shape that you wanted here. A lot of the time, they will ask you to label these, or they will tell you what they are. So you will draw this and say this is a bromine electron. Oops, Br electron. We will draw our circle, closed circle, and say it's a chlorine electron. And then we will draw our X and say that it's a phosphorus electron. And that will make it even clearer what electrons or what electrons belong to which element. So it's just a basic tutorial on how to use those dot and cross diagrams. Let's go back to the PowerPoint. Oh, actually, before we go back to the PowerPoint, one last thing that you should be able to do as well is to turn this into a Lewis structure. In order to turn this into a Lewis structure, all I'm going to do is that I'm going to turn all of these bonded electrons, all of these overlapped electrons, I'll highlight them here, 1, 2, 3. I'm going to turn these overlapped electrons into lines. So I'm going to still have my phosphorus at the center. Let's go back to white. I'm still going to have my phosphorus at the center. Now, instead of drawing this overlap to the chlorine, I'm simply going to draw a single line to the chlorine. If this was a double bond, I would draw 2 lines. If it was a triple bond, I would draw 3 lines. Then I have a line to the bromine and a line to the chlorine in the bottom. And then all of these lone pairs of electrons, I will still draw around my elements, but I would use dots for them. So here we have 1, 2, 3 lone pairs on chlorine. So I would just draw 1, 2, 3, 4, 5, 6. That's 3 lone pairs. This chlorine, again, I have 1, 2, 3 lone pairs. So I would draw my 3 lone pairs. And again, those are already dots, so I'm going to keep them as dots. I have a lone pair on phosphorus, which are X's, but I'm going to keep them on my Lewis structure as dots, because it's no longer a dot and cross structure. And then the bromine has 1, 2, 3 lone pairs, which are here in the dot and cross open circles. But again, on my Lewis structure, there will just be 3 lone pairs as dots. And this is now my Lewis structure for my PCl2Br. So again, very similar to, or very just translating from that dot and cross structure, because again, this is the dot and cross, to my Lewis structure by just using those lines instead of the overlapping valence shells. And notice how those shells, those energy levels, also disappear in the Lewis structure. So now we can go back to our PowerPoint and go back to the next slide. So this is it's a fairly common question on the AICE exam where they ask you to draw a Lewis structure. In this case, dot and cross structure. In this case, they're asking us to draw the dot and cross structure for CS2. I'm going to draw this here because then I'm going to go to the black screen. But the sequence of atoms in the CS2 molecule is sulfur to carbon to sulfur. So they're even telling us that sulfur is first, then it's going to be carbon, then sulfur. Meaning that we have this sulfur connecting somehow to this carbon, this sulfur connecting to this carbon. This is important information because even without knowing what CS2 looks like, we can get an idea of what the structure is. And it says, draw a dot and cross diagram of the carbon disulfide molecule, CS2 being carbon disulfide. We talked about nomenclature in chapter 3. But carbon disulfide meaning 2 sulfurs, show outer electrons only. And now this is very important because we discussed earlier how you could do a dot and cross structure either with just valence electrons, which are the outer electrons, or with the inclusion of those inner shells. Here, they're specifically asking you to only show the outer shell. If you show those inner shells, you will lose the point. You will not score that point because you will not follow in directions. So make sure that you are paying attention to the fact that it says outer electrons only. All right, so we're going to draw it out here, outer electrons only. And we need to remember to follow that. So we're going to draw the carbon disulfide molecule. So I have all my important information here. I know that it's CS2. I know that the order is going to be sulfur, carbon, sulfur. And I know I only need to draw outer electrons. So let's start by drawing the sulfur. The first one, we'll draw this in yellow, since sulfur is actually yellow. So we're going to draw our S here, or sulfur, and then we're going to put our ring around it to symbolize our outer shell. Again, this is outer electrons only, so we're only going to draw this outer shell. Now, sulfur is a group 16 element, and this is very important for you to remember how to do. Sulfur is a group 16 element, meaning it has how many electrons? 6 valence electrons. So we're going to draw these as, we can choose whether we're doing our cross or dots. We'll choose our crosses here. So we have 1, 2, 3, 4. Now I have 2 more electrons. Now this is very important. I have 6 valence electrons. Remember that the lone electrons, the ones that are not paired up, are going to be the ones participating in bonding. So we're going to put those towards the central carbon. So my 2 extra electrons, I'm going to pair them up here and here. Why? This is away from where all the actions are going to happen, right? Where that carbon's in the center. And that's going to be kind of important for you to remember because the placement will make it easier to visualize. Now we do have 2 sulfur, so we're going to draw the exact same thing here on the other side. So we're going to draw another sulfur. And again, we're going to do this circle. And that sulfur we're going to draw again. We have 6 valence electrons, just like in the other one. But when we draw these 6 valence electrons, again, we're going to have we're going to have 1, 2, 3, 4. But again, it's a group 16 element, right? So we want to put those electrons in a way that makes sense. So we're going to draw our X's here and here. Now notice how I inverted. Here I had the lone pairs on the top and left. Here I had them on the bottom and the right. Why? Because, again, I want them pointing towards the inside, which is why I'm not putting anything on the right side. But I want them pointing on the inside so they can pair up with electrons, meaning I don't want them all on the same side, on the top or all on the bottom, because they're going to clash as far as the electrons on the carbon. Now, when we look at the carbon, carbon is a group 14 element, meaning, again, how many electrons is it going to have? It's going to have 4 valence electrons. So when we draw our carbon here in the center, we're going to draw its valence shell. And that valence shell is going to have only 4 electrons. Now, because we use crosses for the sulfur, we do need to use dots for our carbon. Oops. So we're going to do here, dot, 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 and then the 4th one. Now, one of the things that is very important for you to double check is to make sure that in the question they don't tell us which ones they want us to use. So the question reads, draw a dot and cross diagram of the carbon disulfide molecule, show outer electrons only. It doesn't tell us use crosses for carbon, use dots for sulfur, or vice versa. It just tells us use a dot and cross diagram. You will see some questions where they specifically tell you to use dots for one element, crosses for the other. If they do, you need to make sure that you follow those instructions. But in this case, that's not what we're looking at here. So we can choose to use X's and crosses or dots whenever we want, wherever we want. So here, when we have this carbon now, we can see how, very neatly, because of how we chose to do this, the sulfur needs to have 2 more electrons paired up in order to form its octet, its valence electrons. The carbon needs to have 4, and then this sulfur needs to have 2. So if you did this correctly, you can easily see how this will form a bond here, and this will form a bond here. And then how in this sulfur, again, that's 2 carbons on the 2 electrons on the carbon that get used, and the 2 electrons on the sulfur that get paired up, which we needed. And then on the other sulfur, this electron can pair up with the electron on the carbon, and then this carbon electron with this sulfur electron. Again, if you do this correctly, if you orient them in this way, it makes it easier to see. That's why you want to make sure that these electrons on the outer atoms, in this case the sulfur, are pointing towards the inside here, and that you kind of spread them out top and bottom evenly so we can easily overlap. So what's going to happen here? We're going to have our central atom, which is our carbon. So I'll draw the circles first. Overlapping or bonding, let me do this a little higher. Overlapping or bonding with our sulfur atoms. So when I'll do, that was a little off. We're going to draw our sulfur here overlapping, and then our sulfur on the other side overlapping. So we have here our sulfurs on the left and right, our carbon in the center, and then what happens to their electrons? Well, all of the electrons for carbon were shared. Notice, shared, 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 shared. 2 with the sulfur on the left, 2 with the sulfur on the right. Meaning that we're going to have here 1, 2 with the sulfur on the right, and then 2 with the sulfur on the left, which are dots, because the carbon were originally dots. And then the excess on the sulfur, we have 2 that were shared with the carbon for each sulfur. So these 2 were shared with the carbon, so they're going to be in the overlap section. These 2 were shared with the carbon, so they're going to be in the overlap section. And then we have 2 lone pairs for this sulfur. And again, these have to be crosses because they're originally sulfur electrons. And then here we have 2 lone pairs for this sulfur, which again, we need to draw as crosses because they were originally sulfur electrons. And this is our dot and cross structure for the sulfur. For the carbon disulfide. So this is dot and cross. If we wanted to turn this into a Lewis structure instead, which is not part of the question, but I might as well do it since we're here. All we will have to say is, okay, we have carbon in the center, sulfur on the sides. We have 4 electrons being shared, meaning a double bond, or 2 pairs of electrons. So we'll draw a double line here. 4 electrons being shared here. So a double line here, because that's a double bond, because it has 4 electrons. And then the 2 lone pairs on the sulfur, we will draw not as crosses anymore, but as dots for the Lewis structure. And that's our Lewis structure for sulfur, so carbon disulfide. But again, that's not what we're looking for. What we are looking for, what this question is asking for, is our is our dot and cross structure here. So this is our final answer right here. Now you will see how we grade this, right? Because this is what we're looking at now. This is what our dot and cross structure diagram is, where we have 4 electrons being shared between carbon and sulfur, 2 from carbon, 2 from sulfur, and then the 2 sulfurs have 2 lone pairs each, both of them made from X's that we chose to represent the sulfur electrons. So let's go back and we're going to see how that compares to our answer. So if we look at the ammonic scheme here, you see we have the same basic structure where we have 2 lone pairs on the sulfurs, and they chose to use circles for sulfurs and X's for the carbon. So we have 2 lone pairs for the sulfurs that only belong to the sulfur, with 4 electrons between carbon and sulfur being shared. This is another way of showing this where we don't use a circle for the energy level. I do not like this as much because it is very messy as far as what belongs where. Our way of drawing it is a little neater in my opinion. It's a lot easier to see these only belong to sulfur. These are shared, very neat and clean. And then you'll see that this question is actually worth 2 marks. Why? Even though it's one structure, you get 1 mark for sulfurs having 6 atoms, or 6 electrons, and carbon having 4 electrons. So basically for the carbon having 4 X's, and that sulfur having 6 dots. So this comes from essentially you getting a point from being able to figure out how many valence electrons an element has based on its group. And then you get another point for the sulfur-carbon double bonds being clearly shown, meaning that you have that dot cross pairing between the sulfur and the carbon for both the sulfur and the carbon bonds, making it a double bond. So a very generous question here. Even though it's only one structure, we do get both points. And if we look at ours, we have what they require. We have carbon with 4 electrons, 1, 2, 3, 4, 4 dots. And we have the sulfur with 6 electrons, 1, 2, 3, 4, 5, 6, the 6 crosses. 1, 2, 3, 4, 5, 6, the 6 crosses. And we have here the 2 bonds, which are the overlap sections. both of which have 4 electrons, 2 from carbon, 2 from sulfur, showing that double bond very clearly. So we will get full points for doing this. Now, let's keep going. Now, everything we've done so far has been based on what we call the octet rule. And remember, the octet rule is the rule that says that elements are going to bond, in this case covalently bond, in order to gain the electron configuration of a noble gas. That's the common rule, the octet rule. In most covalent compounds, the nonmetals, or sometimes metalloids, share electrons to attain the same electron configuration as a noble gas. However, there are exceptions to this rule because chemistry loves these exceptions, right? It loves having exceptions to things. So the octet rule is no different. The octet rule has exceptions, mainly 2 different types of exceptions. Expanded octets are the first type, which are the most common ones. Expanded octet refers to the fact that the octet rule, in most cases, other than with hydrogen, which only has 2 valence electrons, is going to say that the elements are going to bond to have 8 valence electrons. Well, what is an expanded octet? It's exactly what it sounds like. It's a situation where the atoms, the atoms of the elements are going to have more than 8 valence electrons in the final structure. This is particularly true, this is only true, of elements in period 3 and below. Elements in periods 3 and below on the periodic table can hold more than an octet of electrons. They could, if necessary, if it makes the structure more stable, attain an electron configuration or a bonding configuration where they have sometimes 10, sometimes 12 bonding electrons. And this leads to different shapes, this leads to different compounds. For example, the most common example of this is phosphorus pentachloride, PCl5. In phosphorus pentachloride, or PCl5, the phosphorus, which normally has 5 valence electrons, pairs up with 5 chlorines, which have 7 valence electrons. So the chlorines having 7 valence electrons can only gain 1 more electron, as we can see here in this dot and cross structure, where this chlorine has its 7 valence electrons represented by the dots and 1x from the phosphorus. Well, phosphorus needs to bond 5 different times. So it's going to bond not to just 1 chlorine, but to 5 different chlorines. Well, in that case, or in this case, where phosphorus needs to, in this particular situation, to be stable, bond 5 different times, it shares 1 electron with each chlorine. But if you can count, you will see that in this situation where the phosphorus pairs up with 5 chlorines instead of the 3 that we saw earlier, we are going to end up with 2, 4, 6, 8, 10 electrons in phosphorus. So this is in a case of an expanded octet, where an element that is in period 3 or below, with phosphorus being in period 3, can go beyond the normal octet. And it uses its D sublevel to do this. We're not going to go too far into why this happens. You don't need to know that for the test. But it uses its D sublevel to do this, to gain those extra electrons. This is why this is called an expanded octet, because it's not holding 8 electrons, it's holding more than 8, expanded. In this case, holding 10 electrons. You can tell that this phosphorus will have to have an expanded octet because it is being paired up in PCl5 with 5 different chlorines. Think about it. Every bond has 2 electrons. So if we have 5 chlorines bonded to the central phosphorus, we need to have 10 electrons in total, because even if they form only single bonds, 5 different single bonds will have 10 electrons in total. And you can see here we have 1, 2, 3, 4, 5 different bonds, therefore 10 electrons. This can also be the case with things like sulfur dioxide, SO2. This is not as clear as PCl5, where we can see those 5 chlorines, but in SO2, the sulfur bonds to two oxygens, but then that leaves sulfur with an extra lone pair. Because sulfur and oxygen form double bonds, that's 8 electrons in total, with that lone pair making 10 electrons. Again, making this an expanded octet on the sulfur. This can only happen because sulfur has or is in period 3 or below. Elements in period 2 and period 1 cannot do this. Hydrogen can do this. Oxygen, nitrogen, fluorine cannot do this. Only elements in period 3 and below can form expanded octets. And again, don't think too much about, oh my god, how do I know if the octet is expanded or not? Because when you're asked for a dot and cross structure, when you ask for a Lewis structure, you'll be asked for a Lewis structure of a specific chemical, and they will only make sense if they have that expanded octet, like in the case of PCl5 or in the case of SO2. Now, the other type of exception to the octet rule will then be the opposite of an expanded octet. An expanded octet is more than 8 electrons. Then elements that are electron deficient are elements with less than 8 electrons. This is a more rare case and only happens with two elements, boron and beryllium. Boron and beryllium are the most notable cases where we will have a electron deficient compound. Now you might be asking this and saying, okay, wait, boron kind of makes sense because boron is a metalloid, right? So okay, metalloids are weird. Even though it shouldn't really be in a covalent compound, it can form covalent compounds as a metalloid. But then you might be wondering, wait, why are we even talking about beryllium? Beryllium is a straight up metal, and metals don't covalently bond. Well, one of the things that you will really start to learn, start to realize about covalent bonding is that covalent bonding usually happens between nonmetals, sometimes with a metalloid, but it can actually happen with metals as well. What we call covalent bonding, ionic bonding, is actually not independent black and white topics, but more of a spectrum, where at one end of the spectrum we have ionic bonding, at the other end of the spectrum we have covalent bonding, and up to now in honors chemistry you thought of this as very separate, distinct things. But in reality, it's more of a spectrum where a compound can fall in different ends of the spectrum. Something like sodium chloride is very clearly on the ionic side. Something like carbon dioxide is very clearly on the covalent side. But then there are things that are within the spectrum that lean towards different sides. For example, boron trifluoride, BF3, that we're seeing here, is a covalent compound, but it does lean a little bit towards the ionic side because it has a metalloid in it. Whereas something like BF2, or BEF2, beryllium difluoride, is something that's ionic but leans towards the covalent side because of how beryllium interacts with nonmetals. And there are things that are smack in the middle. We'll learn in a little bit about aluminum chloride, Al2Cl6, and that is smack in the middle between covalent and ionic compounds. Other things that are notable here are things like acids, like HCl, which will be covalent but can act like an ionic compound, and so on and so forth. So we need to kind of start deconstructing the simplified version of chemistry we learned in honors chemistry and start to realize that bonding is not so black and white. It's not things that are covalent or ionic. They can have a bit of a spectrum where things could be covalent with what we call ionic character, or covalent leaning to ionic, or they could be ionic with covalent character, meaning ionic but leaning towards covalent, or some things like AlCl6 are smack in the middle and show both properties of covalent and ionic compounds. So that's why we talk about beryllium here when we're talking about electron deficient compounds, because beryllium can form some very covalent type of compounds. Now, they have less in compounds that are electron deficient. To go back to the original point, we have essentially elements where either boron or beryllium where they don't have all 8 valence electrons that we need. Boron will form electron deficient compounds where boron only has 6 valence electrons and it's still happy and stable. Beryllium will form compounds where it only has, 4 valence electrons and it's happy and stable. Now the one that we will more commonly see is boron, again because the metalloid, so it does form a lot of covalent compounds, but we might see beryllium once in a while as well, so it's good to keep it in mind. So for example, if you're asked to draw the electron configuration of BF3, beryllium trifluoride, boron trifluoride, should I say. Boron trifluoride has 1 boron, which has 3 valence electrons, being a group 13 element, and fluorine, which has 7 valence electrons, being a group 17 element. And we have 3 fluorines because that is what the trifluoride means. So when boron bonds with fluorines, each fluorine needs 1 extra electron to have an octet. So the boron forms 1 single bond to each fluorine, and that leaves the fluorines happy with the octet, but notice how the boron only has, and again I'm going to use my highlighter here, notice how the boron has 2, that is not my highlighter, how it has 2, 4, 6 valence electrons. When boron trifluoride forms, it only forms 3 single bonds in boron, meaning that boron is, again, electron deficient in the sense that in this compound, and basically in every compound boron forms, the boron only has 6 valence electrons. But it's still happy, it's still stable. That's why it's an exception to the octet rule. Whereas the octet rule says that things need to have 8 valence electrons to be happy and stable, boron defies that rule and says, okay, I only have 6 valence electrons here and in most of my compounds, but that's fine. I am happy, I am stable with it. So boron, being electron deficient, having the ability to be electron deficient, is the reason why boron trifluoride can even exist. Because that boron does not need 8 valence electrons, it only needs 6 valence electrons. So those are the 2 exceptions to the octet rule. Electron deficient compounds that can only be made by boron and beryllium, and expanded octet compounds, which are a bit more of a wider variety, which can be made by any period 3 or below element. And usually the atom that will be that will have the expanded octet is that central atom. So notice how here the phosphorus has the expanded octet with 10 electrons, but the chlorines all just have 8 electrons, even though chlorine is in period 3 and could, in theory, create an expanded octet. Usually the expanded octet we look at is for that central atom. Keep going. So let's talk about another kind of subdivision of covalent bonding here, which are coordinate covalent bonds, or what we call dative covalent bonds. So coordinate covalent bonds or dative covalent bonds are a special subdivision of covalent bonding. And this is a special subdivision of covalent bonding where the electrons that form the covalent bond, the single bond usually, although it could be for a multiple one, come from the same atom. What do I mean by that? Normally, when we have something, let's say like oxygen, and it forms a covalent bond, so let's say we have O with 6 valence electrons, and then another oxygen. When covalent bonds are formed, they're normally formed by each element putting in 1 electron to form the bond between the 2 elements. Same thing here with these other electrons. We all put 1 electron from each oxygen, forming the bond between the 2 atoms of oxygen. Well, a dative covalent bond is an anomaly. It's a covalent bond where the electrons are shared, just like in any covalent bond, but both of the electrons in the bond came from the same atom. Meaning that essentially one of the elements, one of the compounds, molecules, whatever is reacting, is so attracted to the other that instead of them going in equally on a bond and putting one electron each, one of those elements will put in both electrons. Now, this is very useful when we're looking at things like the creation of ions or the aluminum chloride that we will look at later. When writing a displayed formula, we show the coordinate covalent bond, or when writing a Lewis structure, another way to say this, we show a coordinate covalent bond by drawing an arrow that you can see here. The arrow head points towards the element that did not contribute any electrons, whereas it originates from the element that gave both of the electrons. Now, this is the most common example of a dative covalent bond or a coordinate covalent bond, which is the creation of the ammonium ion. So the creation of the ammonium ion happens when ammonia, NH3, which we can see here, it's dot and cross structure, reacts with a hydrogen ion, NH plus ion. Ammonia is made from one nitrogen and three hydrogens, which are all single bonded, and these are just regular covalent bonds where one element or one electron came from the hydrogen, one electron came from the nitrogen. And then nitrogen in ammonia has a lone pair of electrons. It has two electrons, we're symbolized here by both dots, that belong to the nitrogen and just to the nitrogen. Well, here's the thing. Remember, electrons, especially pairs of electrons, are going to be fairly negative because that's what electrons are. They're negative. So this right here has a partial negative charge because, or I don't know, putting a partial negative charge, they are negative. I'll just write negative here. And we got to remember the negatives are attracted to positives, right? So if ammonia ever meets a hydrogen ion, an H plus ion, which is essentially just a hydrogen atom without an electron, so it has no valence shell, which is a positive charge, that ammonia with its lone pair of electrons, and now this ammonia is partially negative on this side and partially positive on the hydrogen side, because remember that ammonia is polar. We'll talk about more polarity later, but just from honors chemistry. That ammonia, with its partial negative charge on the electrons, and then the electrons being negative themselves, is going to see this hydrogen positive ion. It's going to be very attracted to it. So that ammonia, that nitrogen, is going to see this hydrogen, it's going to be like, how you doing? And it's going to want to bond to the hydrogen. So when the nitrogen sees the hydrogen, which is positive, with its partial negative electrons here, it's going to say, how you doing? And it's going to invite hydrogen to bond by using that lone pair of electrons that it has. When that bond is created, and we can see that bond right here on the ammonium ion, and this is the ammonium ion, you notice how these bonds right here have a dot and a cross. Why? Because each element, the hydrogen and the nitrogen, put in one electron. But the bond that was created to that H plus ion is now two dots. Why? Because that is a dative covalent bond. Both of those electrons came from the nitrogen. Oops, that's pretty thick. Let me put that down. So this right here, that's the dative covalent bond, or coordinate covalent bond, whichever one you prefer to use. That's our dative covalent bond because both of the electrons came from the nitrogen. And like these other bonds where each element put one electron, both of these electrons came from the nitrogen. And again, just for the sake of nomenclature, this is the ammonium ion, which you should remember from last year, was part of your ions list. This is ammonia, the compound, which is NH3. So if we wanted to transform this into a Lewis structure, again, notice how we have that bracket I want to talk about in a second. If we wanted to turn this into a Lewis structure, I would draw the regular bonds as just lines, like we have here, but this dative covalent bond we would draw as an arrow, with the arrow pointing towards the hydrogen because the nitrogen is the one that put in the electrons. So you can think of this as an arrow of shame. It's shaming the hydrogen. You didn't put any electrons, you didn't contribute, right? And it's pointing towards that element that did not contribute to the bond. So again, that is this right here, that dative covalent bond. Now do notice the charge right? And this is something that's a bit separate from what we're discussing, but good to mention here. Notice how here the ammonia is neutral. It has zero charge. Now we put here zero charge, whereas this hydrogen has a +1 charge. When we combine compounds like this, or when we combine elements or whatever, to make a new ion, in this case, we need to balance out those charges. Meaning that if this is 0 and this is +1, 0 + 1 means that the new compound we create has to still have that +1 charge. That +1 charge didn't get canceled out by anything. It's still there, and so we need to keep it in that compound, or in this case, a polyatomic ion that we're making. That's why when we look at the ammonium, that ammonium has a +1 charge. That's a +1 charge that it inherited from this hydrogen ion, since the ammonia was negative and nothing canceled out that +1 charge. All right? So that's a dative covalent bond. That's very important to know because it's going to play a key role in this next conversation we're going to have in the next slide. And that's a conversation revolving around aluminum chloride. Now, aluminum chloride is a very special molecule. Why? Aluminum chloride is something that you would expect to be ionic, right? So we have a metal and a non-metal. Aluminum is a metal. Oops. So aluminum is a metal. Chloride is a non-metal. So metal with non-metal, you learn that in honors chemistry, that this will normally make an ionic compound, which in this case we will expect to be AlCl3, since aluminum has a +3 charge and chloride has a -1 charge. Well, that's not fully true. Going back to what we said about a spectrum of bonding, aluminum chloride actually falls smack in the middle of this spectrum of covalent versus ionic. So even though we would expect this to be ionic, aluminum chloride falls somewhere here in the middle of this spectrum. So it shows both properties of an ionic compound and properties of a covalent compound. The properties of an ionic compound that it's obviously going to show is things like the fact that it's a lattice, that when we put it in water, it's going to dissociate. But the bonding of it is kind of covalent in nature. Aluminum chloride is a special molecule that starts in that intersection between covalent and ionic. At high temperatures, aluminum chloride exists as aluminum chloride, the ionic compound AlCl3. However, the molecule is electron deficient, since aluminum only has 6 electrons in this form, if we look at it as a covalent compound. So what it does is that at lower temperatures, when you solidify aluminum chloride, it comes together to form what we call a dimer. Now that's a word that you've never heard before. But a dimer is simply just a molecule made out of 2 other molecules that have mixed or bonded together. So essentially what a dimer is the combination of 2 smaller monomers or 2 smaller molecules. In this case, what essentially happens is that the AlCl3 that we just discussed will combine with another AlCl3 molecule to combine into one bigger dimer molecule, which is Al2Cl6. And it does this by forming coordinate covalent bonds, or dative covalent bonds that we just talked about. Essentially, if we look at the aluminum chloride molecule, we have here chlorine, which is happy, right? Chlorine has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. But aluminum has 1, 2, 3, 4, 5, 6 valence electrons. So that aluminum is electron deficient, which it does not very much like. So what happens here? This molecule is going to form a dimer by essentially forming 2 dative covalent bonds. This chloride, which has all these negative electrons, is going to see this aluminum, which is partially positive, because of that electron deficiency. And it's going to use its lone pair of electrons to say, how you doing? And invite aluminum over to bond. So it's going to use its lone pair of electrons to create a dative covalent bond to the aluminum. But here's what happens though. That's one dative covalent bond. Where does the other one come from? This chlorine in this aluminum chloride AlCl3 is also going to have its electrons be attracted towards this aluminum, which is partially positive. So now this chlorine is going to look at that aluminum, which is kind of partially positive. It's going to be like, how you doing? And it's going to be attracted and say, okay, let's bond with this pair of electrons. So these molecules are forming dative covalent bonds to each other in separate sections. One aluminum from this aluminum chloride will form a dative covalent bond to, one chlorine from this aluminum chloride will form a dative covalent bond to this aluminum. This chlorine from this aluminum chloride will form at the same time a dative covalent bond to this aluminum. And that's what creates a dimer. And we can see here, let's ignore that. We can see here how this translates. If we look here, this chlorine goes to this aluminum. We can see that bond right here. See how those two are both X's? Because they both came from the chlorine here. And then we can see this aluminum chloride, this chlorine's dative covalent bond that forms with these two electrons right here, where both of those electrons are X's, because they both came from this chlorine. On the other hand, if we look at any other bond, these three bonds right here, dot X, dot X, dot X, we can see them right here. Dot X, dot X, dot X. These are the normal covalent bonds that were already in the molecule. And then for this molecule, we have dot X, dot X, dot X. We can see those right here. So in this dimer, because this right here, this is what the dimer is. This is the dimer. Ooh, let me make that a little smaller. This is the dimer. And we can see here how we have our original aluminum chloride right here, which was this aluminum chloride, and then our other aluminum chloride here, which was this one, and how they're connected by the creation of these dative covalent bonds. And we can tell they're dative covalent bonds because they're both X's. If we're to draw the Lewis structure, this is a dot and cross structure, and this is a very common question on the test, for you to draw the dative, Lewis structure for the aluminum chloride dimer AlCl6. So again, this is AlCl6 right here. Al2CL6, sorry. Whereas these individual ones are the AlCl3 molecules. And then, so this is a very common question for you to have to draw this dimer structure in dot and cross structures. And then if we wanted to convert that into an Lewis structure, all we will have to do is say, okay, all of these, the yellows and the blues, those are going to be regular covalent bonds. So we're just going to use lines for those. So it's 1, 2, 3, the 3 blue ones right here. And then we have 1, 2, 3, the 3 yellow ones down here, here, and here. And then the dative covalent bonds, the ones in pink, the ones that form between the two atoms, we're going to have here in pink. But notice how these are not lines, these are arrows. One pointing from the chlorine up here to the aluminum, because the chlorine is the one that gave the electrons to the aluminum. And then one down here from this chlorine to this aluminum, because this chlorine gave the electrons to the aluminum. So this is the special case of aluminum chloride and the dimer that aluminum chloride forms, or the dimer that it naturally exists as. So let's look at a paper 1 question that relates not to aluminum chloride, but to all this whole topic in general of bonding. So here we have phosphorus forms a compound with hydrogen called phosphine, pH 3. This compound can react with a hydrogen ion, H+. Which type of interaction occurs between pH 3 and H+? Now here, in this particular case, we have a very key example of what in Cambridge we call a translation of knowledge. meaning that we were never taught this, right? We have not yet had a conversation, or not yet, we will not have a conversation about pH 3. However, we have seen something that is similar to this, and we should be able to translate that knowledge over. Why? We did not have a conversation or ever talk about in these videos about the reaction between pH 3 and H+. Just to give you an idea, the pH 3 will look like this. P with lone pair, H, 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 and then hydrogen plus, just a hydrogen plus ion. We never talked about this. However, this should look familiar to you. Why? We did not discuss pH 3 reacting with H+, but we did discuss NH3 reacting with H+. And this is what we mean by a translation of knowledge. These two compounds are essentially going to behave the same way. Why? In both these cases, we have a group 15 element in the center bonded to 3 hydrogens with a lone pair. Again, group 15 element, nitrogen, phosphorus. And again, we can even see that we don't even need to go as far as drawing the Lewis structure. We can see that as pH 3, this is group 15. So we could replace it with any group 15 element like nitrogen and have NH3 reacted with hydrogen plus. And so we should know that this is going to react exactly the same way. If we have two elements that are in the same group and they're representative elements, we can replace them for each other in a structure and they will behave very similarly. So what happens here? Well, we talked about how the ammonia, NH3, is going to use its lone pair to form a dative covalent bond to hydrogen plus. So I'll be like, how you doing? Because this is partially negative. The hydrogen plus is positive, and how you doing? And use its lone pair to bond to the hydrogen plus. Phosphorus is going to do the exact same thing. So I use this lone pair to be like, how you doing? Because it is partially negative, just like ammonia. And it's going to create a bond to the hydrogen plus. Well, because this bond, both of the electrons are coming from the same from one element, this is a dative covalent bond that is being formed. Or remember, another word for this is a co-ordinate covalent bond. Either or, I mean, they both mean the same thing. So when we look at our answer choices, is this a dipole-dipole force? No. Is this a hydrogen bond? No, because both of these are intermolecular forces. Is this an ionic bond? No, because we don't have any ions. Not yet. Well, we don't have two ions, right? Because we have pH 3, not a negative ion. So this answer is that we have a dative covalent bond. This is a perfect example of translation of knowledge in the Cambridge curriculum, meaning that you never learned about this. And this is why these questions are hard. They're not going to necessarily ask you something you directly learned, but you have the knowledge. If you think about it hard enough, you will see the relationship between pH 3 and NH3 and say, oh, wait, I did not learn about pH 3 reacting with H+, but it should react the same way that NH3 reacts with H+. And that is by forming this dative covalent bond. And that's how we answer this question. All right? So translational knowledge, very important. It does require high level critical thinking because you're no longer just kind of regurgitating or just repeating what you learned. You're actually translating the knowledge into a slightly different situation. That still applies. Whenever you get stuck, look for this kind of relationship where it's a compound that you know about, just that we replaced one of the elements with a different element in the same group. And that was usually a pretty key indication that you have to translate the knowledge you learned for that other element. All right, so let's move on. So let's talk about measuring covalent bonds. So there are some measurements that we make with covalent bonding. Some measurements that we're going to make with covalent bonding, and two of the key measurements we want to make with covalent bonds, are both their bond energy and their bond length. When we talk about bond energy, we're talking about the energy required to break 1 mole of a particular covalent bond in the gaseous state. And the units for that are going to be in kilojoules per mole. So there's a few things we need to dissect here. First of all, the definition is extremely important. This is why it's a separate color here. The energy required, oops, that is not my highlighter. The energy required to break 1 mole of a particular covalent bond in the gaseous state. That is our definition for bond energy. And this is very important because these definitions, especially when it comes to energy, need to be very specific. When we get to chapter 6 and we start talking about thermodynamics, definitions are the key to everything. So when we're talking about breaking or measuring bond energy, the amount of energy it takes to break 1 mole of a particular covalent bond, so we need to have 1 mole of that bond that we're breaking, and it needs to be in the gaseous state. So whatever that bond is in, for example, if we're trying to break an oxygen-oxygen double bond, that oxygen needs to be in the gas state for this, just to call this a bond energy. The units for bond energy are in kilojoules per mole. Why? Kilojoules is our energy unit. So that is a new, we discussed this actually once when we talked about ionization energy, but joules are a unit of energy. So a kilojoule, a kJ, is just 1,000 of those joules, right? 1 kilojoule is just 1,000 joules. That's where the kilo comes from. And then why mole to the negative 1? Well, remember, mole to the negative 1 is the same as saying 1 over mole. So what we're saying here, kilojoules mole to the negative 1, is we're saying kilojoules per mole, or divided by moles. Why? Because it's how many kilojoules of energy it takes to break 1 mole of that particular bond in the gaseous state. That's why the measurement is in kilojoules per mole. Now, the other one that we're going to talk about is bond length. And bond length is a little simpler. It's the distance between the nuclei of 2 covalently bonded atoms. So essentially all bond length is if we have 2 atoms, 1, 2, and they're bonded to each other. I'm trying to make this roughly the same size. And we have our nuclei at the center of these atoms. So we have a nucleus here. Oops, that is not my pencil. So we have a nucleus here and a nucleus here. All that we are talking about with bond length is the distance between the nuclei, meaning from here to here. This distance is our bond length. That is related to atomic radius, but a little bit different because it could be between different atoms, and it's a whole distance, not half of the distance. So it's a way of measuring how long a bond is, because remember, we can't measure the atom itself. So in order to measure bonds, we need to measure the distance between the center of the atom, which is the nuclei. Now, multiple bonds do have an inverse relationship when it comes to bond energy and bond length. And this kind of makes sense. The larger the order of the bond, and by saying the order, which just means single, double, or triple bond, the larger the order, so single, double, triple, then the larger the bond energy. A triple bond will take more energy to break than a double bond. A double bond will take more energy to break than a single bond. And that's pretty straightforward, right? If we have more electrons being shared here in this bond, then it's going to take more energy to pull those apart, because more electrons means more attraction. On the other hand, it has an inverse relationship to how those bonds are going to affect bond length. The larger the order, so triple versus double versus single, the shorter the bond will be. So single bonds are the longest, double bonds are the second longest, and triple bonds are the shortest. And again, why is that the case? The more electrons you have being shared by these atoms, so the more electrons are here, 2 electrons versus 4 versus 6, then the more the forces are going to pull the nuclei towards those electrons. Because the more electrons we have, the stronger the forces of attraction of that nucleus towards those electrons. The more these atoms are being pulled towards the center, then the shorter that distance will get, because the atoms are being pulled towards those shared electrons. So we can see that here, for example. And we do have to compare equivalent things. So, for example, we're comparing carbon-carbon single bonds or carbon-carbon double bond. You see how the energy, the bond energy of the double bond is higher than the energy of the single bond, because the double bond has more electrons. And so it's harder to pull apart because there's more attraction from the nuclei to those electrons being shared. And you can see the same thing with the bond length. The bond length for the double bond is shorter than the bond length for the single bond, which is longer. Why? Because the more electrons you have in that double bond, the more attraction towards the center, which shortens the distance of that bond versus a single bond. We can see the exact same thing here with the comparison between carbon and oxygen double bond single bond, where again the double bond has a larger bond energy than the single bond does, and a shorter bond length for the double bond versus a longer bond length for the double bond. Now, what I wouldn't do, and this is something you should not ever do, is I would not compare the carbon-carbon double bond to the carbon-oxygen single bond. You should never compare something like that, because the radius of these atoms is going to play a part in both the bond energy and the bond length. So you can just compare the double bond, single, and triple bonds of different atoms. They do have to be between the same two atoms that we're comparing. So that is something to keep in mind. Alright, so our last slide of the video here is bond properties and reactivity. Now, bond length and bond energy both are a result of the strength of the attraction of the nuclei to the atoms and to the nuclei of the nuclei to the electrons in the atoms are sharing. The larger the number of electrons in the bond, the more attracted the nuclei are going to be to the electrons, and therefore the stronger and shorter the bond. And again, that just goes back to that little diagram that I drew earlier, where if I have one atom here and then another atom that shares electrons with it, and then at the center of that atom we have our nuclei, which I'll just draw a little positive here and here, then the number of electrons is going to make a difference. If I only have 2 electrons here in the center, then I'm going to have a weaker attraction towards the center, meaning a weaker bond, lower bond energy, and a shorter bond, than if I add another 2 electrons to that bond, which is then going to create even more attraction to the center. And then if I make it a triple bond and add a third layer of electrons, or a third pair of electrons, then that attraction will be even stronger between the nuclei and those electrons, making that bond even shorter and more powerful, or having bond energy. Short bonds with really high bond energies are harder to break than those of longer bonds with weaker energies, right? Because that's what bond energy tells us. Bond energy tells us how much energy a bond requires to be broken. The higher the bond energy, the harder it is to break that bond, and so the more unreactive the molecule will become. Because if we have the definition of an unreactive molecule is one where it's really hard to make it break or make bonds. For example, nitrogen, N2, is a prime example of this. Nitrogen is just 2 simple atoms of nitrogen with a triple bond connecting them. The triple bond in that nitrogen is such a strong bond because it is a triple bond. There's 6 electrons, or 3 pairs of electrons, in between those 2 nitrogen atoms, forcing them together very strongly. The bond strength, or the bond energy, of a nitrogen triple was 994 kilojoules per mole, almost 1,000 kilojoules per mole. because it's so hard to break the nitrogen-nitrogen triple bond, nitrogen is very abundant in nature because it's so hard to react it. Nitrogen makes up 70% of the air we breathe because there's very few things that can break it apart. There's very few bacteria that can actually break down that nitrogen-nitrogen triple bond. Or the only other source of like really breaking down nitrogen that we have is lightning. Lightning has so much energy that it can actually force the nitrogen-nitrogen triple bond to break. But think about that statement. It takes a lightning bolt to have enough energy, 994 kilojoules of energy per mole of nitrogen, to break that triple bond. So now we do need to keep in mind, this is only because we're talking about nitrogen by itself. That's why nitrogen is so unreactive, because the bond energy is really high, thanks to the fact that it has a triple bond. But when we're talking about comparisons, we have to be careful. When we're comparing the bond length, we need to make sure that the atomic radius of the atoms we're comparing are similar. Bond length is the distance between the nuclei. So like we said, I'm going to erase this here. It's the distance between, the nuclei of the atoms. Go back. So, okay. So, because it's between the nuclei of the atoms, we have to consider the nuclei of the atoms itself. So, the radius of the atoms itself. So, if we have two small atoms overlapping with a single bond, we cannot compare that to two large atoms overlapping with a triple bond. Why? If we had two larger atoms, whether they're single, double, or triple bonded, right? So we say here we have a single bond, which should in theory be longer than, let's say it's just a double bond here. In theory, this single bond should be longer than this double bond, but if our radius of the atom is smaller, it doesn't matter whether it's a single bond or a triple bond or a double bond. If the atom itself is bigger, the distance between the nuclei will also be bigger. So, for example, we could compare the single bond, let me do this in a different color. We could compare the single bond in fluorine to the double bond in oxygen to the double bond or triple bond in nitrogen. Why? The atomic radius of fluorine, oxygen, and nitrogen are similar, 72, 73, 70 picometers. So we can see here how from the single bond to the double bond to the triple bond, we see that bond length trend that we expect, where the single bond is the longest, the triple bond is the shortest, and then the double bond is somewhere in the middle. And again, this only works because we're comparing atoms that have very similar atomic radius. But look at what happens when we talk about hydrogen. Hydrogen has a much smaller radius. So this here will be hydrogen, whereas this might be something like oxygen. Hydrogen has a very small radius. So even though it has a single bond, which should in theory be the longest of the bonds, its bond length is shorter or shortest out of any of the ones we have in this chart. Why? Not because of the bonding, not because it has a single bond, because in theory that should tell us that that's the longest, but because the atomic radius is the shortest or the smallest out of all of these. And a smaller atomic radius will just have a much smaller bond length. Because the bond length, again, is the distance between the nuclei, meaning that radius does play a part. So be careful when you're comparing the double, single to triple, or what we call the order of the bonds, because you can only compare the order of the bonds when it relates to bond length if the atomic radius of the atom is similar. So that's something else that you need to keep in mind when you're making these comparisons. It's a lot to keep in mind, so you have to make sure that you're keeping a mental track. Go in steps. When being asked to compare molecules and you notice that they have different orders of bonds, single, double, versus triple, the first question you should ask yourself if we're talking about bond length is, okay, what is the radius of these atoms? And we talked about atomic radius and its trend in chapter 2, but what is the radius of the atoms? Does it make sense to compare them? Essentially, are they in the same period, right? Fluorine, oxygen, nitrogen are all in the same period, so they have very similar atomic radius. Hydrogen is in period 1, where these are in period 2, and that's why we cannot compare them to each other. These are in period 2, so we can compare these to each other, but with hydrogen being in period 1, we cannot compare hydrogen to these other 3 because that atomic radius will be very different. And that stems from our conversation on the trend of atomic radius that we had in chapter 2. So keep these things in mind when you answer these questions. I know it's a lot to keep track of, but as you do more practice, as we do more practice questions, as we discussed in class, you will slowly start to internalize this information and subconsciously start looking for it. All right? That is it for section 3 of chapter 4. I will see you next time for the next video.